Hello and welcome to our presentation. My name is Sergei Proskurin. I am a PhD candidate at the Technical University of Munich. Today, it is my pleasure to present our paper titled xMP, Selective Memory Protection for Kernel and User Space. The paper is the result from the collaboration with my colleagues Marius Momeo, Ahmed Gamamnia, Vasilis Kemerlis, and Michalis Polychronakis. Today, we're going to talk about how we have used virtualization extensions to assist primitives inside operating systems to thwart data-oriented attacks. At this point, we would like to highlight that even though we employ the system's virtualization extensions, we do not explicitly use or need a fully fledged virtual machine monitor to protect the operating system. Instead, our operating system primitives directly utilize the system's virtualization extensions to enhance selected components of the OS with the ability to defend against data-oriented attacks. Data-oriented attacks have become a serious threat. They completely avoid changes to the control flow. Instead, they modify non-control data to perform arbitrary computation. This makes them highly difficult to detect. For instance, back in 2014, the Heartbleed bug of the OpenSSL library has shown us the true potential of such attacks. This attack has disclosed an immense amount of sensitive information without leaving any traces behind. Because of this, data-oriented attacks have to be taken seriously. Generally, to mount a data-oriented attacks, attackers have used memory corruption vulnerabilities to gain read and write primitives into the victim's address space. They use chains of data-oriented gadgets, for example, to disclose sensitive information or escalate privileges without violating the application's control flow. In this way, data-oriented attacks can remain undetected despite code reuse mitigations. And this is why, with our work, we emphasize the need for practical primitives that allow to eliminate such threats. We introduce selective memory protection, or short xMP primitives, to assist operating systems in thwarting data-oriented attacks. In a nutshell, we use virtualization extensions of Intel to provide Linux with the following primitives. First, we partition selected memory regions, which hold sensitive information, into disjoint xMP domains. Second, we isolate xMP domains by enforcing fine-grained memory permissions. And third, we obstruct corruptions of pointers to xMP domains by equipping them with context-bound HMACs. In the end, these primitives allow Linux to protect sensitive data in xMP domains. Also, to avoid interactions with the VMM, we use Intel's fast ePTP switching and virtualization exception capabilities. In this way, we lend Linux the ability to dynamically switch among different xMP domains without outsourcing the entire logic to the hypervisor. To implement the xMP primitives, we utilize the alt-P2M subsystem of the Xen hypervisor that we describe in the following. Please note that we use Xen alt-P2M only to reduce the implementation overhead. The provided functionality is not bound to any hypervisor. In fact, it could be even implemented as a kernel module. Let us briefly refresh our memory on virtualization technology. Normally, a VMM uses only one set of second-level address translation tables, which is short for SLAT or EPT on Intel, to translate the guest physical to host physical memory. In other words, one set of EPT tables defines the guest's view on the physical memory. As we can see on the slide, this view is defined mainly by access permissions to the physical memory. If we change the permissions in the global set of EPT tables, we will inevitably affect the global view on the memory as it is perceived by all vCPUs in the guest. Instead of using only one view on the guest physical memory, the Xen alt-P2M subsystem allows to dynamically allocate and switch between different views. By switching the views, we can efficiently change memory access permissions without having to walk the EPTs of a global view and without affecting the views of other vCPUs. And this is exactly the feature that we use as a central building block for xMP. Let us turn our attention towards the first xMP primitive, in which we use Xen alt-P2M to partition memory into disjoint xMP domains. As we know, the hardware allows only one alt-P2M view, which is a set of EPT tables, to be active at a given time. At the same time, we would like to configure multiple xMP domains to guard disjoint memory regions, and these disjoint regions cannot be accessible at the same time. For instance, if one xMP domain guards the kernel's hardware encryption key, it must not be accessible when we enter an xMP domain that holds a private key of a user space application. My point is that we cannot simply associate one xMP domain with a single alt-p2m view. Instead, we have to propagate access restrictions of all xMP domains across all available alt-p2m views. Specifically, this means we require two alt-p2m views to set up one xMP domain. We dedicate one view, the restricted view, to unify the memory access restrictions of all xMP domains. This is the default view on all vCPUs. We use the second view to relax the restrictions or unprotect a given xMP domain and to allow access to its data. To accommodate n xMP domains, we define n+1 alt-p2m views. This is shown on the slide. By entering a specific domain, we relax the permissions of the memory region that belongs to this particular xMP domain. All other xMP domains remain in their restricted state. In the example on the slide, we enter the xMP domain n, which grants read-execute permissions on the lowest two guest frame numbers, or short GFNs. At the same time, we propagate execute-only permissions to the same GFNs in the remaining views. This means that only if we enter the domain n, we will be able to access these GFNs with read-execute permissions. The second xMP primitive allows us to equip the Linux kernel with the capability to configure xMP domains. For this, we have extended Zen to allow Linux to use the alt-p2m subsystem. But then again, we only use Zen as a vehicle to set up alt-p2m capabilities for Linux. In a truly no VMM setting, this could be done by the OS kernel itself. In addition, we use Intel's fast ePTP switching and the virtualization exceptions feature to allow Linux to take over several EPT management tasks. For example, to enter a specific xMP domain, Linux can execute the vmfunc instruction to switch into the corresponding alt-p2m view. At the same time, unauthorized access to the memory in xMP domains will trap into the ingest virtualization exception handler and not into the VMM. In summary, this xMP primitive provides the operating system with the flexibility in defining policies and fine-grained permissions without outsourcing any logic into the VMM. The final xMP primitive ensures the integrity of pointers to sensitive data in xMP domains. This primitive aims to obstruct, for example, privilege escalation attacks, which try to redirect pointers to high-privileged objects inside xMP domains. Specifically, we use ziphash-generated HMACs to authenticate selected pointers. Ziphash itself is optimized for short inputs. This makes it perfectly suitable for our purposes. We truncate the generated HMAC to the most significant bits of the pointer's address. For instance, on a system with 4 levels of page tables, addresses occupy the first 48 bits. The most significant 60 bits are sign-extended and remain unused. This allows us to use this part of the virtual address to store a truncated HMAC. Further, we lock down one read-only key per xMP domain so that a domain cannot access a key that belongs to a different domain. For this, we remap the guest frame numbers of each xMP domain such that every xMP domain translates the same guest physical address, which holds the key, to a different machine physical address. In this way, every time the guest kernel enters an xMP domain, it will use the key that is dedicated to this domain only. Also, since the address of the key does not change across xMP domains, we embed the key's address as an immediate instruction operand that cannot be controlled by adversaries. Finally, to ensure that pointers cannot be redirected to other objects inside the xMP domain, we additionally bind them to a specific context that is unique and immutable. For example, we can bind thread-specific pointers to the address of the thread's task struct instance. In this way, we establish pointer integrity and ensure that the authentication succeeds only in the right context. Having established the concepts behind the xMP primitives, we integrate them into the Linux memory management system. In other words, we enhance the Linux memory management system with capabilities provided by the system's virtualization extensions. In this way, we establish a foundation that is required to thwart data-oriented attacks against selected memory regions in both user and kernel space. In particular, we target the body and the slab allocator, as we can see on the slide. The body allocator uses the GFP flags, which stand for Get Free Page, to indicate the conditions, the location, and the way how to allocate a set of physically contiguous pages. Any other allocator in the system uses the body allocator to acquire physical memory. We cause the body allocator to place the allocated memory pages into a specific xMP domain. Specifically, we encode an xMP domain's index into the GFP allocation flags. In this way, the allocator receives sufficient information to inform Zen outp2m and to place the allocation into the provided xMP domain. In our implementation, we have used 8 free bits of the GFP flags to encode the xMP domain's index. The slab allocator builds on top of the body allocator. It maintains caches of slabs with frequently used kernel objects of the same size. For instance, the kernel uses the cred.jar slab cache to maintain all instances of the struct cred data structure. We extend the slab allocator in a similar way to the body allocator. This means by encoding the xMP domain's index into the allocation flags, we can instruct the slab allocator to place selected slabs with all instances of a particular kernel data structure into an isolated xMP domain. We also allow user processes to protect selected memory regions. For this, we introduce 4 new system calls that allow processes to allocate, free, and isolate memory in xMP domains. We do not use the unprivileged vmfunc instruction in user space. Instead, we dedicate a system call, namely sys.xmp_enter, which updates the xMP per thread state in the kernel and only then enters the requested xMP domain. In this way, the kernel can detect unauthorized xMP domain switches on the next context switch. Finally, having equipped the different Linux components with xMP, we have to preserve process or thread-specific state on context switches. Without going into details, we extend the user and kernel thread state. Specifically, we provide dedicated state fields that present the xMP domain in which the user or kernel thread resides at a given time. In this way, the scheduler can switch to the saved xMP domain of the thread that is about to be scheduled next. To avoid switching to a potentially corrupted xMP domain index, we bind the state to an immutable context. Similarly to protecting the integrity of pointers, we equip the particular index fields with hmags for the associated domains. Depending on the scenario, the use context to which we bind the xMP state fields can be, for example, the address of the task struct instance, which is unique and immutable. In this way, the scheduler can verify the hmags before entering the xMP domain and thus obstruct a potential attack. As part of our work, we have applied the xMP primitives to establish and controlled access to the process page tables and credentials. Our goal was to leverage xMP to prevent attackers from illegally modifying the contents and the pointers to any instance of both data structures. At the same time, xMP has to allow the kernel to update these structures from authorized locations. To achieve this, we use the modified body allocator to place new sets of page tables into a dedicated xMP domain. Similarly, we use the modified slab allocator to protect all instances of struct cred in another xMP domain. In both cases, we enforce read-only permissions from the outside of the respective xMP domain. Also, we extend the kernel's process and thread creation functionality to protect the integrity of each pointer to the process page tables and credentials. For instance, we equip the thread's PGD pointer to the root of page tables with an hmag and verify its value on every context switch. The same applies for every pointer to the cred data structure. In this way, we prevent attackers not only from illegally modifying the contents of both data structures, but also from redirecting their pointers. We also apply xMP to guard sensitive data in selected user space applications and libraries. For instance, we apply xMP to protect against the heartbleed bug in the OpenSSL library. We would like to refer everyone to our paper for more details. We have evaluated our work by applying xMP, among others, to isolate page tables and process credentials of a Linux guest. The guest was running on top of the Zen hypervisor. We have measured the performance impact of the xMP when applied to each data structure individually or in a combined setting. For this, we have used a set of micro and macro benchmarks, which are shown on this slide. Without going into details, we can say that xMP introduces minimal overhead for real-world workloads and applications. In this category, we have measured overheads between 0 and around 12%. In addition, we have measured the impact of an increasing number of xMP domains. For this, we have integrated xMP into the Linux namespaces framework. This allowed us to isolate selected system resources of containers. We have customized the Phoronix Hackbench scheduler stress test to create groups of processes and place them into individual xMP namespaces. Processes in the same xMP namespace isolate their page tables inside the corresponding xMP domain. This means that page tables of processes in different xMP namespaces are isolated by different xMP domains. As we can see on the slide, we have measured the overhead in up to 250 xMP namespaces. Interestingly, what we can see here as well is that by increasing the number of xMP namespaces, the scheduling overhead amortizes the overhead provided by xMP. In summary, xMP sets the ground for efficient, selective memory isolation primitives for user and kernel space. For this, we have combined Intel's fast ePTP switching capabilities and virtualization exceptions. By additionally protecting the integrity of pointers to sensitive data inside xMP domains, we establish a strong defense against data-oriented attacks. We are happy to announce that a part of our prototype is open source. Please check it out and let us know what you think about it. Thank you very much for your attention. Do you have any questions?